Thank you very much for the introduction. And first of all, I would like to thank the organizers for inviting me to this wonderful conference held at a very nice place. Actually, this is the first trip abroad after 2.5 years. So my topic today is making optical lattice clocks compact and useful for real-time world applications. This background image is our laboratory almost 5 years ago. 2 clocks occupy whole lab, and we are now making them compact. When I was preparing this presentation, I noticed that my first trip to Canada was 24 years ago. And I found my old abstract for the poster presentation. So it was the timing when we started my group. And presenting a poster at ICAP is an excellent motivation for a young group. And I was one of them. We pushed our strontium cooling experiment, and 2 months later, we submitted. So this is the very beginning of a long journey of strontium optical lattice clocks. So today's topic is think about real-world applications of state-of-the-art atomic clocks. This is already given by a wonderful talk this morning by Simon. If you have a 10 to the minus 18 uncertainty, this corresponds to a gravitational redshift of 1 centimeter difference. Then, clock can be a new sensor. Then, our concern is how quick can we measure the height difference, or how small can we make it? So, you are already familiar with the atomic clocks. So, atomic clock, what do we do? We stabilize the laser frequency to the atomic transition frequency. This is what we do. Long coherence time of atoms give very narrow spectrum of like 1 Hertz. The important thing is sub-wavelength confinement of atoms suppress Doppler effects. So we trap the atoms, so-called Ramsey regime. And this is demonstrated for the first time for an ion in a Paul trap, as described by Eckhart on Monday. The disadvantage of the ion case is the limited number of ions. They are limited by the quantum projection noise. So this is the motivation why we started optical lattice clock. If you collect many atoms, then we can measure the time quicker. This is the idea. The essence of the optical lattice clock is the engineered redshift. In atomic clock, we measure signet SDF ground state to the TPP0 excited state. If you confine the atoms in an optical lattice, the standing wave of light, this perturbation modifies the transition frequency. Our trick is that this is the Stark shift, and this is the Stark shift of the upper state. If you tune the dipole polarizability of the ground state and excited state equal, then this Stark shift perturbation can be canceled out. We call this special wave frequency the magic frequency. By tuning to the magic frequency, this differential Stark shift cancels out. Then we can measure true atomic transition frequency. after 20 years of research, 10 to the minus 18 uncertainty was achieved. But laboratory clocks may become more and more complicated to be used in the real world. For the real-world applications, we need a long-term and stable and transportability are required. For example, chronometric labeling, or dark matter search by a clock network, or redefinition of a second, given by the previous talk by Helen. So, my talk includes our way for a sustainable development of our clocks and research. We push our laboratory equipment into a black box in collaboration with industrial partners, boosted by the Mirai Fund project with the Japan Science Technology Agency's budget. So, we call the first generation compact clock, whose volume is 1,000 liters. Using this clock, we tested the gravitational redshift at Tokyo Skytree. And now we are packing this clock into a van to be transportable. We are now also developing a second generation clock, which is much smaller, 250 liters in volume. And it's in evaluation. And in the last part of my talk, I will discuss a new spectroscopic scheme, which is named Longitudinal Ramsey spectroscopy. In this spectroscopy, we hope to achieve 1/tau scaling of clock instability. It means we can measure something quicker. For the first step, we build a continuous lattice-trapped atomic source. So this is a photo of our first generation clock, built with the industry partners. We packed lasers and electronics in the lab into these 19-inch mountable boxes. These two boxes operate this clock, and this is another clock. By comparing two clocks, we can say something. This is already a familiar experiment. If you lift up one of the clocks by 1 meter, then what will happen? This movie is quite useful to explain our situation to a general audience. So this is the beat note of the clocks. When you set the clock at the same height, it agrees at the 10 to the minus 18 level. And if you lift up one of them by 1 meter, then upper clock ticks faster by 47 millihertz. This shows a pair of clocks serves as a real-time gravitational potential meter. As I said, you can resolve 1 centimeter height difference. This is the inside of our first generation transportable clock. We set the optics on a water temperature control breadboard, and we made a very robust external cavity laser. And this is our physics package, oven and Zeeman thrower, and this is inside the main chamber. We have a bow tie cavity. And we roll the atoms here and transfer the atom into a blackbody radiation field. to protect the atom from backbody environment. Backbody radiation shift is huge for strontium atom. It amounts to 2.2 Hertz at room temperature. And this gives uncertainty of strontium clock. But by using that kind of trick, we can reduce the uncertainty down to low 10 to the minus 18. By taking these two clocks to a broadcasting tower in Tokyo, which is called Tokyo Skytree. It's like Toronto Tower. We set one of the clock on the ground floor and the other on the observatory floor at 450 meters and compare the clock. Upper clock ticks faster by 21 Hertz, and this gives a gravitational redshift. To test the formula, we measure the gravitational potential difference in collaboration with Geospatial Information Authority of Japan. They measure the gravitational acceleration and height difference by conventional leveling technique and get the gravitational potential difference between the two clocks. And we compare. And in this experiment, we determine this alpha to be this number on the level of 10 to the minus 5. This is the best gravitational redshift test on the ground. If you combine this result with the satellite experiment, we can say gravitational redshift is tested at 10 to the minus level in the range of 500 meters to 10,000 kilometers. So for us, more important thing is that this is the first demonstration of 10 to the minus 18 level clock outside the laboratory. This is a very important step toward future applications of this kind of accurate clock. So, in Mirai project, we are interested in the technology transfer of a clock to industry partners. We design compact and robust and extremely accurate clock to explore new applications. And manufacturers, Shimazu and JEO, develop compact and reliable electronics and lasers and physics packages. We have also collaboration with NTT, it's a telecom company, and they help networking clocks with their fibers. We have strong collaboration with user group, Meteorology Institute, of course, and we work with geophysicists to discuss new applications of millimeter to centimeter level height measurement in view of volcanology and seismology. This is an example. With collaboration with NTT, they developed a PLC-based optical repeater. This is already given by the previous Helen's talk. We need a fiber repeater to convey our clock signal to a remote station. For that purpose, NTT built a planar right wave circuit-based Doppler noise canceller. This works very good because of this very good stability of the PLC. And this is a demonstration to link the 240 kilometer, and link stability was 10 to the minus 18 level after 3,000 seconds. And this is not very good because of the Tokyo's special situation. We are living in a very noisy town. So this is a photo assembling our second generation clock with industry partners. This is new laser and electronics package, very small. And our new physics package is even smaller. And this is the new package, just 40 liter. And we measure the stability by a so-called three-corner hat measurement using first-generation clock. We achieved 10 to the minus 18 stability in about 1,000 seconds. This instability is not excellent. This is because this measurement was before the installation of blackbody radiation shield. This floor was given by a blackbody radiation. And this is a benchmark of the transportable clocks. Our first generation clock, 1,000 liter, the accuracy was 5 times 10 to the minus 18, and newest one, total volume is 250 liter. And we hope to push the uncertainty down to 1 times 10 to the minus 18, or even better. So we are now making our clocks more transportable. We are NTT to link the fiber up to Mizusawa area, which is 500 kilometers north of Tokyo. We had a big earthquake 11 years ago in this area. And in the earthquake, this area, ground level was subsided by 30 centimeters. 11 years ago, 30 centimeters. And after that, we see an uplift of 3 centimeters every year. So we want to test the dynamic chronometric leveling for this effect. If we take our clock there this year and next year and measure the frequency, and if it corresponds to this one, this is a demonstration. And also, given by a Henen's talk, in Europe, they have a big fiber network connecting PTB, SHIELD, and INRIM and NPL. We are planning to take our transportable clock to NPL next year. Then we can compare clocks and verify the identity of clocks over the continent. This will be the important step for the redefinition of the second. And this is the stability of our transport on-vehicle clock. We installed first-generation clock into a van. It's a small van, Toyota Hi-Ace. This is because we have a collaboration with IC, which is a group company of Toyota. So this is the stability. Stability goes down to 7 times 10 to the minus 19, even if you install the clock in the car. This is very good. This means if you measure clocks for example, 3 hours, then you can resolve 7 millimeter height difference. So we are exploring the potential applications of optical lattice clocks in a plate subduction zone, namely Japan. Japan Islands located at the plate boundaries, and we are suffering from big earthquake and eruption of volcano, and etc. Is, from another point of view, are a good place to test dynamic chronometric leveling. We are pursuing an application to seismology that complements conventional GNSS, Global Navigation Satellite System leveling. If we make compact clocks to sense millimeter height difference here in a time scale of hour to many, many years, which is good for clocks, then we can detect, for example, a very small slow slip, which is a precursor of a big earthquake. So, using a GNSS leveling survey, this line can be investigated with a certainty of 1 centimeter. This is a motivation why we want to focus this regime. So, my last topic is here. We want to change the power law of clock instability. Why the optical lattice clocks potentially improve the clock stability by observing many atoms? The stability heavily relies on the stability of clock lasers, as impressively demonstrated by Junye using a cryogenic silicon cavity. And we are wondering if there are a way to make best use of the potential stability of optical lattice clocks. One of the ways is make a super radiant laser. And another way is zero dead time operation of clocks by combining the clocks. And instead, we proposed the longitudinal Ramsey spectroscopy. I will explain it. So the idea is, if you apply a standard time sequential measurement and correct atoms and measurement again, then the instability improves as 1 over square root of the number of measurements. This is the origin of 1 over square root tau. But if you continuously monitor the clock transition and control the phase of the laser, then stability improves as inverse of measurement time. So we want to make a continuous clock. So our goal is to make a compact and stable clock. We like a small one. So start from a very small cavity, like 3 centimeter long cavity. Then the thermal noise limited stability is around 10 to the minus 15. But if you quickly improve the stability by 1 over tau, then it leads to a quantum projection noise limit of, for example, 1,000 atoms in 15 minutes or so at the low 10 to the minus 19. This is a line we want to draw. So we know that Ramsey spectroscopy on an atomic beam allows continuous measurement and control. In Ramsey spectroscopy, they use atom oven and thermal atomic beam, and this atom flies this way, and 2, 4 transverse beams. Atoms interact with these 4 beams and close this atom interferometer, and they get a signal. They have a good stability, but even in the very recent experiment, their final stability is limited by the mechanical instabilities of these probe lasers and residual Doppler effect. And this limits the thermal Ramsey scheme to go below 10 to the minus 16. Then, our idea is, how about using a single probe beam and lambdic confined atoms, which is realized by a moving lattice technique. Because we shine clock laser longitudinally, I named longitudinal Ramsey spectroscopy. The point is how to excite 2 times by pi over 2 pulses. This is the essence of Ramsey spectroscopy. We used local magnetic field. And this is the scheme. We assume 88 strontium, for example, which has a highly forbidden clock condition. And we place 2 magnets here and there. We assume lattice-trapped atoms and moving at the velocity something. If the atom across this magnet mixes the clock upper state and dipole around state and give finite transition moment for the atom, then it gives a half-wave pulse. Then here, atoms freely evolve. Then, when the atom passes through the magnet, it gives another pi over 2 pulse. And we will see a Ramsey fringe like this. Even if you measure atomic state in a projective way, atoms are still alive here. We can use this atom for another short Ramsey period. By combining this and this information, it means very fine Ramsey signal and broad Ramsey signal, we can extend the fine Ramsey signal for larger frequency range. This gives you a large frequency capture range. The experiment is not yet done, but this is the simulated stability, starting from 10 to the minus 15 level clock laser, and stability goes down by inverse of tau and reads here. So the important device for this longitudinal Ramsey spectroscopy is a continuous lattice-trapped atomic source. Previously, we make deep cooling of atoms in a time sequential way. And Schreck group successfully demonstrated to extend to apply the cooling by spreading in space. And we are now exploring a new scheme of continuous cooling by using metastable states of strontium. We make first cooling using strong transition, and for the atoms decay redux to a metastable state, this is trapped by magnetic field, and then we apply narrow line cooling using mid-infrared transition. The good point for this is that this cooling laser is very far detuned from strontium transition, and this gives 10 to the minus 20 level redshift for the clock. So this cooling is compatible with the clock. So it's almost time. So this is more magnetic optically trapped atoms are loaded in a magnetic trap, and by shining mid-infrared laser, we cool them, and we load atoms into a lattice. At this point, we are successfully trapped the atoms into a moving lattice, also in the triple P0 state. So, in principle, this cooling is compatible with the operation of optical lattice clock. So this is the team we are working with. This continuous cooling scheme is developed by these Takeuchi, Chiba, and Suji, and Okada. So this is the summary. We packed laboratory clocks into boxes down to 250 liters. And transportable clocks resolves sub-centimeter height difference. And we proposed longitudinal Ramsey spectroscopy, and we are pushing this experiment now. And in the long run, we hope to put many of our lattice clocks and networks to see what is happening underground. Thank you very much for your attention.
Thank you very much, Professor Katori, for a very interesting and also impressive talk about the transportable clocks and all that. So we have time for a couple of questions, 2 or 3 questions.
So this idea of a continuous Ramsey is really exciting with the 1/t scaling of the Allen variance. So I'm trying to make a connection to what I think I already understood about the way clocks would work. The usual thing I think of is that something like an active hydrogen maser is going to give 1/t because of the fact that it's providing the frequency standard by oscillating. And systems like a traditional cesium clock or any of these other clocks where I probe go like 1/√t. So how do I understand in the context of those two examples of 1/t and 1/√t, how do I understand your case?
Yeah, thank you very much for an excellent question. So, in principle, I think this scheme is exactly the same as the old cesium beam clock. Old cesium beam clock, they have microwave horn here and detect the cesium state here. I think this is exactly the same. And I think in principle, if they remove the source of uncertainties, they will also demonstrate 1 over tau. I don't know, but I think exactly the same as the OCDM clock.
Okay. Maybe we can have lunch together.
Maybe we have time for another question. Over here. Oh, get 2 more then.
Hi, thank you for the interesting talk. I was wondering if you know if there's any size, weight, power advantages for compactifying an optical lattice clock versus a trapped ion clock.
Yeah. So I think the big difference is the stability. So you like to compare trapped ion clock and lattice clock. So in lattice clock, by using many atoms, we can reduce the quantum projection noise by square root n. That is the advantage. So we are good at, in principle, measuring the frequency difference in a very short time period. And this is why we think about dynamic chronometric wavelength. Ion clocks can be very accurate, but it takes much longer time to measure some frequency difference.
Yeah, thank you. I also feel this slide is really exciting, but I want to make sure I understand your proposal on this. Is that a correct understanding that the Ramsey power over 2 pulse is kind of controlled by your magnetic field? Or?
Yes.
Oh, wow.
Yes.
I just wonder how, in your maybe estimation, how hard it is to calibrate this power over 2 and where the divergence angle of your atomic beam matters for this Ramsey measurement?
So the first thing is, we need an accurate magnetic field, and we calculated assuming a good current source. So, good current source, the uncertainty of less than 1 times 10 to the minus 18 will be achievable. So this is one thing. And another divergence thing. So in reality, we build this moving lattice inside the bow-tie cavity. So the range can be very long, say 10 centimeters something. So we can neglect the divergence of the beam.
Thank you.
I guess one more quick question from June.
I just want to make a comment, regarding Bill's question and Hidetoshi's answer. I feel like if the probe laser, or in the old days of a cesium clock, the microwave at the time is a local oscillator. As long as their coherence time is longer than the separation of the 2 zones divided by the velocity of the beam, then you can do this continuous speed. You just cannot let the phase evolution go beyond a single fringe of your Ramsey. Once you go beyond it, then you have to do this repeated measurements, which will average as 1 over square root of tau. But as long as you can control it, in some sense, depending on your probe laser, will dictate the separation of your 2 magnetic field region. As long as it's below it, then it's a phase-tracked system. Is that correct way of thinking about it? That's why cesium clock, if they had a better microwave oscillator in the old days, they could do exactly the same thing as you're proposing. But I think the local oscillator limits how far you can separate these 2 regions.
Yeah. So, in this case, to answer your question, this multi-zone measurement helps. If you set the magnet closer, this gives you a very wide spectrum. So even if the initial laser coherence is not very good, this broad spectrum captures the frequency.
Yeah.
Then improve the coherence, then we can measure the fine spectrum in this longer region.
Yeah.
Okay, thank you. Thank you, Professor Katori. And let's thank again both our speakers.